Welcome everybody to example 8 on page 144. And this is an example where we're going to try to actually calculate the orthogonal projection of a vector onto a subspace. Okay, so let's read example 8 together here. So we're starting with a subspace W that's the span of two vectors in R3. And we'd like to find the orthogonal projection of 1, 1, 1 onto W. So this vector y is not in the subspace W, but we're going to try to find the best approximation of y that actually is in the subspace W. Okay, so if you look back at our theorem that deals with orthogonal projections, in order to do this, we need to start with an orthogonal basis for our subspace. Okay, so that's our first step here. How do we do that? Well, the Gram-Schmidt process is our way of doing that. Okay, so we'll start with our basis step. Actually, let's first give our vectors names. So W1 and W2. There's a basis for W. We'd like to replace it with an orthogonal basis. So if we start with the basis set, V1, or basis step, V1 is going to just be W1. Okay. And then to calculate V2, we're going to go back to the formula from theorem 6.4, the Gram-Schmidt process. You can look back at that. So to calculate V2, we're going to start with W2 minus the inner product of W2 with V1 over the length of V1 squared times V1. Okay, oh, and V1, let me go ahead and just write in what V1 is. Okay, V1 is 110. Okay, and we're talking about just the ordinary standard inner product in R3, so I'm trusting that you can do these calculations. And the dot product upstairs is going to be 3. Down below, that length squared is going to be 2. Okay, and if you do that calculation, you wind up with -1/2, 1/2, and -1. Okay, we talked about before, at this step in the process, when you get ugly numbers like fractions, 1/2, it's convenient to scale your vector. That's not going to change the fact that V1 and V2 are orthogonal to each other. So let's go ahead and do that. We'll scale that. Okay, so rename this V2 tilde, and the V2 that we're actually going to choose is going to be twice that, just to get rid of those over 2's that we're seeing. So we multiply our V2 tilde through by 2, we're going to get -1, 1, and -2. Okay, and so just to highlight, V1 and V2, that would be an orthogonal basis for W. That gives us a starting point. Okay, so now we are ready to use theorem 6.6 to actually calculate the orthogonal projection here. Okay, and so what I'm about to write is just going to be the conclusion of theorem 6.6, the formula as to how we express U as a combination of the vectors in our orthogonal basis. Okay, so U is going to look like the inner product of Y, which is 1, 1, 1, with V1 over the length of V1 squared, okay, times V1, plus the inner product of Y with V2 okay, over the length of V2 squared times V2. Okay, we just need to do that calculation. It involves taking some dot products and adding some things together. So I'll let you double check all of that. We're going to get a 2 over 2 times 110. Okay, and then over here, let's see, dot product up in the top here is going to turn out to be a -2 over 6. Okay, and if you do the arithmetic here and add this up, here's what you wind up with. 4/3, 2/3, and 2/3 again. That number that we found is the orthogonal projection. Okay, now I want to make just a note on this. Okay, now it's important to realize that this vector that we got, the u, we may not scale that, okay, because the orthogonal projection is a unique vector. It's the unique projection of the vector y that we started with into our plane. Scaling it would change that, so I want to make sure that everybody realizes that. Okay, because u is unique. All right. Okay, and could we confirm this? Just maybe convince ourselves that our answer is plausible here. Okay, let's do just a quick confirmation. Just convince ourselves that this answer is reasonable that we have. One way to do that is to calculate the vector z. Remember how the orthogonal projection formula kind of looked like this: y equals u plus z. It took our vector y that we started with and split it into one part that's in w and one part that's in w perp. If we take that formula and solve it for z, let's just see what that would be. We know that y is 1, 1, 1, and we just calculated u to be this vector. Okay, if you subtract those, here's what you get. Whoops, that's a minus 1/3. Minus 1/3, 1/3, and 1/3. That's the vector z, and if we've done everything right here, that z should be in w perp. How would we check that just to see if that's really the case? Well, being in w perp means that that vector should be perpendicular to everything that's in w, including the two vectors that sort of built w way up at the beginning. So I'm going to scroll up for just a second here. W was the span of these two vectors. And so we could check by asking the question, is z perpendicular to both of those two vectors? If it is, it's going to be perpendicular to everything that's in w. All right, so let's just do that. So starting with 1, 1, 0, what would happen if we took that inner product? Notice that we're going to get minus 1/3 plus 1/3. That's 0. So far, so good. And what about the other vector? Okay, in the initial basis for w that we had. Okay, well, you can see that dot product, negative 1/3 plus 2/3 minus 1/3, that's also 0. Okay, and those two calculations confirm that z is indeed in w perp. Just giving some credibility to the answer that we got up here.